So these next few slides show you how these standard reduction potentials were determined. I mentioned through the use of the standard hydrogen electrode. The most important thing about this slide is right here in the upper right-hand corner, that to get the cell potential, the standard cell potential of a cell, you just need to add your cell potential of your cathode plus the cell potential of your anode. Those usually come from that table of standard reduction potentials. One you will have to flip, and it will be your anode. You'll have to flip that and change the sign of your cell potential because one has to be the reduction and one has to be the oxidation. And just remember to flip the sign when you flip that reaction. This next slide is just how copper was determined as well. Again, just the standard cell potential of the cathode plus the standard cell potential of the anode, and that's where we come up with 0.34 volts. So this next slide, slide 23, has a example problem. Okay, what is the standard EMF of an electrochemical cell made of a cadmium electrode in a 1 molar cadmium nitrate solution and a chromium electrode in a 1 molar chromium 3 nitrate solution? We know it's chromium 3, and that's important because in that list of cell potentials, you're going to see chromium 2 to chromium metal, you're going to see chromium 3 to chromium 2, and you're also going to see what we need here, chromium 3 to chromium metal. So make sure you check those carefully when you're looking up those cell potentials. So if you want to try this on your own, you can just pause the video. If not, I'm going to go through here and show you the solution and sort of talk you through that as we go. So the first thing you're going to need to do is look up your two reductions from your list of standard reduction potentials. In your textbook, this is on page 845. It's that same picture that was in your PowerPoint a few slides before that you could go back and look at that. Remember, you can always use your online textbook through Cengage Brain, the MindTap Reader, and you can find it there as well. So here are the two halves. You have cadmium plus 2 electrons yielding cadmium metal. The standard cell potential there, reduction potential is negative 0.40 volts. And you have chromium 3 plus 3 electrons to chromium to give you a standard cell potential of negative 0.73 volts. So now here it's kind of, you have to determine which one's going to be the reduction and which one's going to be the oxidation. And it's actually pretty simple. Whichever one has a greater standard cell potential, in this case, more positive or the higher standard cell potential, will remain the reduction, and the one that has the lesser reduction potential will change into the oxidation. So in this case, the chromium, because it has a less potential to be reduced, will be our oxidation, and we will flip that half, the chromium half, and we'll keep the cadmium half as is. Okay, so here's just another way to sort of look at that. Cadmium is the stronger oxidizer, so cadmium will oxidize the chromium. So here's our oxidation, the chromium going to chromium 3 plus 3 electrons, and what will be our reduction will be the cadmium. It will stay, as I mentioned, as written, 2 electrons plus cadmium plus 2, yielding cadmium metal. Now, as you can see here, the electrons are not quite equal. So in order to write the balanced equation, it still is important, even though it's not going to change the standard cell potential, that we multiply our reactions to get our electrons to be equal. So we're going to multiply this first reaction by 2 and your second reaction by 3. Then we can add that all together and we get our final balanced equation as 2 chromium as a solid plus 3 cadmium ions, 1 molar. Again, that's a standard cell, is a 1 molar solution, yielding 3 cadmium solid plus 2 chromium 3, again, at 1 molar. Now, to determine the cell potential, very simple. Just add your cell potential of your cathode and your anode. The one thing that we have to make sure that we do is that we change the sign right here because we wrote this now as an oxidation, so we flipped it. So that's going to be a negative 0.40 volts plus a positive 0.73 volts to give us an overall answer of 0.33 volts. So that's your final answer. A lot of times you'll be asked to provide the balanced equation as we did up here. So it was a good sort of example of doing that.